Now the only thing that's different is that we have already settled that the tendency portfolio has to be the market portfolio. Right? So the capital asset pricing model uses this relationship, but the beta that you compute is the beta with respect to the market portfolio. Because in our world, that is the tendency portfolio. Right? Let's see which page this was. This was page 86. I just want to reference this here. So this is the result from page 86 with market portfolio as tendency portfolio. If you want to write it down in terms of excess returns, that would be mu k minus RF equals to question where you want to write the beta mu m minus RF times beta k. And this part here in parentheses also has a special name. This is called the market risk premium. And then we have our standard expression for the beta. Again, as a reminder, that's also like a regression coefficient, so that's pretty convenient for measurement. So now we have a formula where basically if you want to know the expected return of something, and that will be something that we use as a discount rate in the present value method, you basically need to find out three things. You need to find out what's my risk-free rate, right? So people will maybe kind of use the same time horizon as their investment horizon is. So if you want to invest for 10 years, kind of think of what's the risk-free rate over that time period. Then you would need to know what's your market risk premium. So empirically, you would probably go with the very, very long time series of market returns, right? Or whatever proxy you have for the market portfolio. Determine what's the long run average historical return of that, and use that for mu m. There's quite some debate around how you exactly do that. You use geometric averages or arithmetic averages. There will be a big difference. So, say in Germany, the geometric average is roughly 8% per year in the long run. The arithmetic average is probably 11 or so. So there is a bit of a difference. It should also be kind of adjusted to your investment horizon. And then you need to measure the beta, right? We've already looked at how volatilities are changing over time, so betas do that as well. I have a paper on this, a research paper on this, basically showing that betas behave very differently in terms of a crisis or a recession than in normal times. Right? Basically, if you have, the intuition is very, very simple. If you have a recession, everything goes down at the same time, right? So what does that imply for the beta? Everything's much more in line with the market, so all the betas are close to 1. Right? So small betas increase towards 1 and the large betas fall. They become smaller and go also towards 1. Right? So it's a nice pattern that we can actually see in the data, that the betas are time variant and they behave different in normal times and in crises. Okay, so this is what I meant with this is the most applied formula in practice, because if people want to apply the present value method, they want to know what's my discount rate. So usually they kind of settle on these three parameters. Some corporations, the planning departments that do capital budgeting, they even have kind of numbers that they provide to the sub-departments, say these are the numbers that in our company we have to work with. So maybe use the long-term average for the risk-free rate, 3.5%, and maybe use as the market risk premium kind of 7 to 8%. And our company beta in the long run is maybe 0.7 or so. And then everyone knows, okay, this is the things that I have to plug in my formula. And then I have a discount rate to use in the present value approach. Kind of when I want to kind of start a new investment, I have to get past the investment committee. That's the one that I have to use in my business case and my computations. Right, so it's a very, very essential number, very often used. So really the only difference that we make now to the previous chapter is that we plug in a very special portfolio for the tangency portfolio, which is the market. Right? And from this you can already see how we can test the theory. You can basically look at, is the market portfolio indeed the tangency portfolio? Are these two things the same? Then our theory is good. If they're not the same, we should reject the theory. Now, one thing that might look a little bit surprising here is, well, I showed you the derivation, and we saw that the beta came out of this, but like in portfolio theory, on our x-axis as measured for risk, there was the volatility, right? So where's the volatility gone, right? It's not in here, so suddenly we have the beta here. So if you look at the equation, it says that the volatility is not relevant for the expected return. It's only the beta. Well, there's a relationship between the two, right? So the higher the beta, also the higher the volatility. So it's going in the same direction. I would show you a formula to link the two together. But it's kind of not obvious where the volatility is gone, right? And why there's only the beta. So I need to kind of show you that point here as well. But it's important to note here that for pricing, only the beta is relevant. It's the only risk relevant for pricing. So to extend this language, you could think of priced risk and unpriced risk, right? So there's some part of the volatility, which is risk, right? But it's not included in the prices. And there's a reason why it's not included in the prices that I would like to show you. Before we move on to kind of this next step, any questions regarding the form? Okay, so you already see the name here on the slide, and maybe let's move on to the graphical illustration next. This formula here is a line, like a linear function again, that we can draw in a picture, and this is now the so-called security market line. So maybe let's take some time to compare the pictures from portfolio theory on the left and the capital asset pricing model on the right. So this will be our portfolio theory picture. And this is our capital asset pricing model picture. Now, of course, we draw the picture on the left already with the prices of the equilibrium. Right? So we have derived very thoroughly last week how to get the picture on the left. Right? You kind of form the efficient frontier, you determine the tangent line. Now you know how to do that mathematically. But the question is, how do we get the security market line? How do I know how to draw that? Well, the easy answer is, if you want to draw a straight line, you only need 2 points on the line, right? So maybe let's identify 2 points on the left that we can easily draw on the right-hand side. And easily drawing means, because we have now the beta on the x-axis, is the point that we just have to know the betas. Right? So think about 2 points on the left of which we know the betas. Well, the first one is the risk-free asset. It has zero volatility. And the zero volatility always corresponds to zero beta. So we can just put this on the y-axis as well. And the next point will be our tangency portfolio here. What is the beta of that? Well, in equilibrium, tangency portfolio is the market. And we have already determined what the beta of the market should be. If you compute the beta of a variable with itself, we get 1. Right? So we have a second point that we can draw here. And now we can just draw a straight line through it. That's the security market line. So the graph on the left here is the CML, capital market line, and the one on the right is the security market line. Just be very careful kind of in terms of what's on the axis here. Never draw these things in the same picture. There are different kind of representations. So we've already discussed what the slope of this line here is. That was the Sharpe ratio of the tangency portfolio or the market. So what is the slope on the right-hand side picture? Well, if you go back and use the expression up here, so the slope of the SML is the excess return of the market, UM minus RF, technically speaking divided by the beta of the market, which is 1 here. But I want to write it down this way, so you have an equivalent of the Sharpe ratio, which has an excess return in the numerator and the risk measure, now it's the beta in the denominator, and this fraction here, this ratio has a name, and this is the so-called Treynor ratio. Right, so we have the Sharpe ratio where the volatility is written down here, and the Treynor ratio has the beta written down here. So the slope of the capital market line is the Sharpe ratio of the market portfolio now in equilibrium, and the slope of the security market line is the Sharpe ratio of the market portfolio where the beta of the market is obviously 1. But you can compute the Treynor ratio of any asset if you like, and that's how you would do it. Right, it's the excess return of the asset divided by the risk measure relevant for pricing. So let's annotate this a little bit further. So we have our tangency portfolio on the left, and on the right we have the market and tangency portfolio. It's obviously here the same as well, because we are now in equilibrium. So let's maybe think about where do we find other assets in that we maybe have. Let me kind of draw and put in 2 assets. We put one in here and one in here.